Hey everyone, and welcome to this explainer. Okay, let's jump right in. When we think about the digital world, we usually imagine something, well, weightless, right? We call it the cloud, or cyberspace, or the ether. It all sounds so invisible, just floating somewhere above us. But here's the reality. The virtual world is actually heavier, hotter, and hungrier than we ever really imagined. Today, we're unpacking a massive paradox, how the invisible artificial intelligence revolution is literally demanding the most massive, concrete physical infrastructure build-out of our entire generation.
So that brings us to a pretty wild question. Is the cloud actually made of steel? We tend to view AI as just code, algorithms on a screen. But I want to challenge that perception right out of the gate. Sustaining artificial intelligence isn't really a software problem anymore. Actually, scratch that. It's definitely not just a software problem anymore. It has rapidly turned into the absolute greatest physical engineering and energy challenge of the 21st century. The sheer scale of this is just fascinating. On an individual level, an AI transaction is actually super efficient. Generating a single text prompt takes about 0.24 watt-hours. That is tiny. It's tens of times less energy than playing a modern video game or streaming a movie in high definition. But the real danger? It comes from massive concentration. Because when you aggregate thousands upon thousands of servers and you run these complex AI models at maximum capacity 24 hours a day, you create this completely unsustainable electrical density. A single hyperscale data center can devour as much energy as tens of thousands of homes combined. Just think about that.
And you can see exactly where this is heading. In 2024, U.S. data centers consumed around 183 terawatt-hours of electricity. But by 2028, just 4 years later, that demand is forecast to skyrocket to a staggering 580 terawatt-hours. This isn't just some gradual uptick. It is an explosive upward curve that is basically rewriting every single industry forecast out there. And our current power grids, they simply were not built to handle this kind of hyper-concentrated massive load.
So, what exactly happens when this virtual demand hits our physical limits? That brings us to Section 1, Real-World Breaking Points.
Because this systemic danger is not just theoretical. Let's look at July 2024. In Virginia's famous data center alley, a massive crisis was narrowly avoided here. Walk through this sequence of events with me. First, a relatively simple piece of hardware, a surge arrestor on a transmission line, fails. That causes a rapid voltage fluctuation. Now, because these new data centers are highly automated to protect their super-sensitive equipment, 60 massive data centers simultaneously sense the drop and instantly disconnect from the grid to switch to their backup generators. And boom, an astonishing 1,500 megawatts of demand just vanishes from the grid, just like that. This sudden drop caused a massive overvoltage spike that nearly triggered a cascading regional blackout. It completely exposed just how fragile our power grid really is when it's forced to deal with the synchronized, automated behavior of these tech facilities.
To avoid catastrophic blackouts, the tech industry knew it needed a drastic solution, which brings us to Section 2, Resurrecting the Atom.
You see, the tech giants quickly realized something critical. While solar and wind are fantastic, they just don't provide the 24/7, uninterrupted, firm base power you absolutely need to run a hyperscale AI data center. So, their solution? Resurrecting the American nuclear industry. And the U.S. government is strongly backing this shift, issuing executive orders in May 2025 that set a massive, ambitious goal, quadrupling the country's nuclear capacity to 400 gigawatts by the year 2050.
So how exactly are these tech companies securing all this power? Well, we're seeing two landmark approaches right now. On one hand, Microsoft signed a binding agreement with Constellation Energy to literally reactivate the historic 3 Mile Island plant by 2027. No way, right? But yes, it's happening. On the other hand, Google took a completely different path. They closed a historic deal with Kairos Power and the TVA to develop next-generation small modular reactors, or SMRs, aiming for commercial operation by 2030. They are literally buying the power before the plants even come online.
Let's zoom in on that Microsoft deal for a second, because the sheer physical and economic scale of this is just breathtaking. The reactivated 3 Mile Island, which is now renamed the Crane Clean Energy Center, is scheduled to return to full power in 2027, which is actually ahead of schedule. This single project adds 835 megawatts of clean energy to the grid, creates over 3,400 jobs, and it's projected to inject a massive $16 billion into the Pennsylvania economy. It's just a striking example of how virtual AI needs are driving these absolutely massive, real-world industrial projects.
But as you might guess, you can't just plug a massive data center into a nuclear plant without making some serious waves. And that sparks Section 3, the bureaucratic battlefield.
Tech companies are in such an extreme rush for power right now that they've started using a highly controversial strategy called co-location. Basically, this means tech companies literally build their data centers right next door to existing power plants. Why? So they can siphon the energy directly from the source, completely bypassing the slow, bureaucratic nightmare of connecting to the public power grid. Amazon Web Services tried to do exactly this, attempting to acquire 480 megawatts directly from the Susquehanna nuclear plant in a massive deal with Talon Energy.
But regulators actually stepped in and hit the brakes. In November 2024, the Federal Energy Regulatory Commission, or FERC, shocked the market by rejecting the Amazon deal in a 2-to-1 vote. And their reasoning makes a lot of sense. If Amazon completely bypassed the grid's transmission fees, they'd essentially be getting a free ride on the system's infrastructure. Regulators calculated this move could unfairly transfer up to $140 million in costs every single year onto the shoulders of ordinary everyday ratepayers. So, FERC blocked it, mandating that data centers absolutely must pay their fair share to use existing infrastructure. And this regulatory fight highlights a much deeper, more personal issue. That brings us to Section 4, the human and social toll.
The crucial point here is how all of this plays out in our own backyards. Just look at these numbers. In Maryland, consumers were recently forced to absorb a collective $2 billion fee just to upgrade regional transmission lines. And the kicker? Those upgrades were largely needed for data centers located in neighboring states. Then, on top of the financial hit, the environmental draw is just immense. Modern AI facilities can evaporate up to 5 million gallons of local drinking water every single day just to keep their servers cool. And then there's the noise. Massive, constantly running cooling towers emitting this incessant noise pollution, completely upending the quiet of American suburbs. So yeah, communities are understandably revolting.
And, fascinatingly, right alongside this physical fatigue, we're seeing a parallel wave of behavioral exhaustion. As communities fight the physical machines of the AI era, society at large is pushing back against the digital toll. By mid-2026, 44 U.S. states had passed laws to ban or restrict smartphone use in schools. It's this undeniable societal reaction to combat severe mental health issues and the social isolation that these very networks and artificial intelligence systems have amplified. We are quite literally hitting our limits, both physically and psychologically.
So how do we possibly balance the unstoppable ambition of the tech industry with the very real limits of our physical world? Let's look at Section 5, Engineering Our Reality.
To prevent a complete collapse of public support, a major systemic intervention took place. In March 2026, the White House orchestrated the Ratepayer Protection Pledge. Under pretty intense pressure, Silicon Valley giants signed this agreement, which basically requires them to independently finance their own power generation plants and any necessary transmission upgrades. The goal here is simple, and it's completely impartial: to ensure that this monumental, incredibly expensive expansion of artificial intelligence is paid for by the tech companies themselves, rather than causing a massive spike in the monthly electric bills of the American middle class.
Which really brings us to the core takeaway of this entire explainer, captured perfectly by this quote. The technology challenge for the coming years will not just be programming smarter algorithms, but mastering heavy civil engineering. The relentless march of artificial intelligence has definitively proven that the virtual economy has a massive, undeniable material footprint. To build the future of software, we first have to tackle nuclear energy, pour millions of tons of concrete, lay thousands of miles of high-voltage wire, and seriously respect the limits of our water supplies in our local communities.
And that leaves us with one final, pretty provocative thought to consider. Can our physical world actually sustain our virtual ambition? Every single time we generate a new AI image, run a complex prompt, or just ask an algorithm a question, we are pulling on a massive physical chain of steel, water, and uranium. The cloud is very real, and it is firmly anchored to the ground we walk on. Thank you so much for joining me on this explainer today. Keep asking questions, keep looking closer at the physical costs of our digital future, and I will catch you next time.